All right, so section 1.3, we're going to be talking about real numbers and how we can classify them into groups and the number line. Let's go ahead and start off with a couple definitions. This first definition is for a set. And so a set is just a collection of objects. And so sets can be sets of numbers, which is what we'll work with most of the time, or it can be a set of colors or something like that. And we'll take a look at a set as soon as we define one more thing. So this next definition is for an element. And this is different than elements that you'll see in science classes, but this is just an object in a set. And so these aren't necessarily actual objects. This is an example of a set that just uses numbers. So we use curly brackets here, and I'm just going to list out the numbers 1, 2, 3, 4, and 5. And so you're always just going to list the objects, numbers, whatever they are, just singly with commas in between. And so as an example, this number 3 here would be an element. And this entire thing is the set. And so now we're going to use this to classify numbers. So we can classify numbers into different sets. And so the first set we're going to look at are the natural numbers. And another name for these are the counting numbers. And so the reason why they're called the counting numbers or the natural numbers is because it's what we naturally use to count objects. So if you think about when you start counting, you don't generally point at thin air and start at 0. You usually start at 1 and then go up from there. So 1, 2, 3, 4, if you're counting, say, cars in a parking lot. So the set of natural numbers is the numbers 1, 2, 3, 4, and so on. And so these dots here just represent that this goes on forever. And notice there are no fractions or decimals. We don't usually count half of objects. And so those are our natural numbers. The next set of numbers, and these are all just going to kind of build on one another. These numbers are called the whole numbers, and whole numbers are just all of the natural numbers plus 0. So we're just going to start at 0 and go up from there. So 0, 1, 2, 3, and so on. After the whole numbers, again, just building onto this, we're going to have the integers, and these are what we're going to be working with most of the time. Integers are all of the whole numbers and their opposites. And now 0 doesn't have an opposite, so that's the only one we're not going to have the opposite of. So these are going to go all the way down to negative infinity, and then we're going to negative 3, negative 2, negative 1, 0, 1, 2, 3, and so on. And again, notice they're all whole numbers, not whole numbers in this sense, but whole numbers in that they don't have fractions or decimals. Next set are called the rational numbers. And so we're going to define these a little differently. We can't actually write these down as a set because it would be way, there would be way too many numbers in there for this to work well. But notice in the word rational, we have the word ratio. And so ratio is just a fraction. And so rational numbers are numbers that can be written as a fraction. And in the book, you might see this as numbers that can be written as the quotient of two integers. Quotients are just division. So I'll also say quotient here. And we're going to see, or we're going to write this as a over b, so just a fraction. And we're going to specify that b cannot equal 0 because, like we'll see a little bit later, we can't divide by 0. And so some examples of rational numbers, some obvious ones that you can write as fractions. Fractions themselves, so 1/2, even an improper fraction like 4/3. The number 2 is also a rational number because we can write this as 2/1. So we're still building on these previous sets. All of these integers are also rational numbers. The number 0.333 repeating is also a rational number because we can write this as 1/3. And same thing as a decimal that terminates, so 0.4, because we can write this as 4/10. And so the key thing here for rational numbers, this is going to be all fractions, and these are all positive or negative, integers, repeating, and terminating decimals. So repeating, think this one here. Terminating, if it ends, we can also write it as fraction. So the only ones that aren't going to be rational are things like pi. So pi is that 3.1415, goes on forever, doesn't have a pattern to it. So that one's going to be irrational. And we'll define that in a second, but let's go ahead and try graphing some rational numbers on a number line. All right, so let's go ahead and graph -3, 17/8, -2.75, 1.5, and -3/4 on a number line. And so if you see this on the homework, you should be given a number line with correct spacing. So I'll go ahead and give that to you here. Let's go ahead and draw out a number line. We'll have 0 in the middle. Then we'll do 1, 2, 3. And on the left, -1, -2, -3. And so now our first one, -3, nice whole number. It's going to go right here. And I'll go ahead and label this because we're going to have a bunch of numbers here. 17/8. And so this one here, it's hard to tell what this number is just looking at it, but let's go ahead and change it to a mixed number. So remember, 8 goes into 17 2 times. That's 16, so there's a remainder of 1/8. And so this is going to be a little bit after 2, so we'll just go ahead and put it here. These don't have to be exact. So this is 17/8. -2.75, this is going to be, you go to -2 and then 0.75 of the way to 3, so it's going to be right there, a little bit of a tight squeeze. 1.5, we're going to go to 1 and then half of the way to 2, so this is 1.5. And then -3/4, that's not quite -1, it's going to be 3/4 of the way there, so it's going to be about right there, a little bit before we get to -1. All right, so now our last set of numbers are the irrational numbers. And one thing to note here is that all numbers are either going to be rational or irrational. You can't have a number that's both rational and irrational, and if it's not rational, it has to be irrational and vice versa. And so this is just the opposite of what we said before. So these are numbers that can't be written as fractions. And the way to think of this one, let's look at a couple examples and we'll write that down. Any square root of a number that's not a perfect square, so square root of 2, square root of 3, square root of 5. Perfect squares we'll talk more about later, but all of these are irrational. Pi, like I said earlier, is also irrational because we can say it's approximately 3.14, but we can't write out the whole thing because it goes on forever and there's no pattern to it. And then another one is the number E. And E is approximately 2.718, but again, it goes on forever. There's no pattern to that one. All right, so all of our numbers that we're going to be working with are either irrational or rational, and together those two groups make up the real numbers. And so the real numbers are all rational and irrational numbers. And the other way to think of this is that they're numbers that can be put on a number line. So even if we think about, let's say, the number pi, it's going to go a little bit after 3. You might not know exactly where it goes, but we can still put it on the number line. Numbers that aren't going to be real are numbers that we'll see in Math 96 if you take that class, because we'll be working with imaginary numbers, but we don't have to worry about those for this class. All right, so this example, we're going to be working with a bunch of real numbers here. We want to list the numbers that belong to each group, or that belong to each set of numbers. And so we're given a set of numbers here. We're given the set -7, -4/5, 0, square root of 3, 2.7, and 13. And we want to go ahead and list out all of the whole numbers first. And so the only one we're not going to do is the natural numbers. And then we'll go ahead and list out the integers, followed by the rational numbers, the irrational numbers, and the real numbers. And so remember that these all build on each other with the exception of irrational numbers. Those are kind of their own set here. So we should be able to just kind of add 1 or 2 to each group as we go along. So let's start with the whole numbers. Remember, these are all of our natural counting numbers, 1, 2, 3, 4, and so on, and 0. So we have 0. We don't want any negatives right now, and 13. So we got 0 and 13. Just says to list, doesn't have to say we have to list them as a set, so we don't need those curly brackets. Integers, we're going to add in the opposites to these, but we're still not going to have any fractions or decimals, so we can add in -7, but we're still going to have this 0 and 13, so -7, 0, and 13. The rational numbers are going to be all of these integers, plus any that can be written as fractions. So this one here, -4/5, is a fraction. Square root of 3, this is one of those irrational numbers. 2.7 is a terminating decimal, so that one is also rational. So we have -7, -4/5, 0, 2.7, and 13. And just to keep the ordering nice, I'm putting them in numerical order. If you put them in a different order, that's perfectly fine. The irrational number is the only one here that's left that is not rational, so square root of 3. And then the real numbers are going to be all of these numbers combined, since we don't have any imaginary numbers here. The way to see if you have an imaginary number is you'll see the letter I next to the number, which you shouldn't see in this class at all. So the real numbers are going to be all of these. All right. So now let's start talking about how we can figure out how to order these. So figuring out if numbers are smaller or larger than one another. So determining, spelled that wrong. Determining the order of real numbers. All right, so let's take a look at this number line here. Our number lines, like we saw in the one that we previously looked at, we'll usually put 0 in the middle unless we don't need it. But on the right side, we're going to have all of our positive numbers. The left side is going to have all of the negative numbers. And so as we go to the right, they get larger. And as we go to the left, they get smaller or more negative. And so in this example, we want to go ahead and just circle the smaller number. And so I'm going to go ahead and write these out, and then I'll give you guys a little second here as we go to see if you can circle the correct one before I say them. So -2, 2, just want to circle the smaller one. Number 2, 0, -6. Number 3, -4, -5. And number 4, -2/5 and -1/10. So that one's the trickiest one. Just take a quick second there, work through the first 3 if anything, and then we'll take a look at that last one. And so number 1, because we have a positive number, that one has to be larger, so we'll circle the -2. In number 2, any negative number is smaller than 0, so circle -6. In number 3, the larger the more negative a number is, the smaller it is. So -5 is smaller than -4. And for this one here, just like we did once before, to compare these, it's going to be easier if we get a common denominator. And so 10 can be our LCD, so we're going to go ahead and change -2/5. And so we can change this one. We change that 10, or change the 5 to a 10, multiply by 2. 2 times 2 is 4. And so we have -4/10 versus -1/10. They're both negative, so we want the one that looks larger, so the -2/5 is going to be the smaller number. All right, these next ones are similar to those that we just did, except they're true or false questions, and we're going to use those less than or greater than symbols that we looked at previously. And so number 1, I'm going to write these out. I'm not going to say the symbols because that'll give it away, but I want you guys to take a look at these and see if you can just figure out if they're true or false. So number 1, -2, this symbol, 4. Number 2, 6, pointing to the right, -3. Number 3, -9, pointing to the left, -12. Number 4, -4, pointing to the right with a line under it, -1. And number 5, -6, pointing to the left with a line under it, 0. So take a quick second there and see if those are true or false. And so number 1, we've got -2 is less than 4. This is true. So negative smaller than a positive. Number 2, 6 is greater than -3. This is also true because a positive is greater than a negative. -9 is less than -12. If these were positive numbers, that would be true, but they're negative, so this is false because -12 is smaller. -4 is greater than or equal to -1. This one's going to be false because -4 is not greater than or equal to -1. And then finally, -6 is less than or equal to 0. This one's true it is less than 0. It doesn't have to be equal to. All right, so now the last little parts of this section, a couple more kind of definitions. Additive inverse. And so additive inverse is just a fancy way of saying opposite. And so normally I'll just say opposite. Just make sure you're familiar with additive inverse. I know my math lab might use that. So if we go ahead and look at another number line, put 0 in the middle. If we put 3 on the right and -3 on the left, these two numbers here are additive inverses or opposites. So they're just two numbers that are the same distance away from 0. And so if we see this -3, normally we'll read it as -3, but you can also think of this as the opposite of 3, which in that case it's not super helpful to think of it as the opposite of. But if we have -3, this is the opposite of -3, because we have the opposite of -3, and the opposite of -3 is +3. So just think of these negatives as canceling out. So for this set of examples, we want to go ahead and find the additive inverse of the following. Number 1, let's go ahead and find the additive inverse of 15. So additive inverse of 15, just -15. Number 2, additive inverse of -9 is +9. The additive inverse of -0.1, +0.1, so same with decimals. Same with fractions. If we have 1/2, the additive inverse is -1/2. For this one, just remember, and this is really important, so this will come up time and time again, if you're putting a negative with a fraction, make sure it goes out in front or on the top or the bottom, but not both. So we could have written this as -1/2, or 1/2, or like we did with the negative in front, 1/2. But we can't write this as -1/2. So like we'll see soon, negative over a negative makes a positive. So this would not be a negative fraction. And then finally, the additive inverse of 0, we don't really have -0, so this is just 0. All right, so now last part of this section is on absolute value, which we'll see when we're evaluating expressions. We're doing order of operations questions, and then this will come up again in 96. But what absolute value is the distance from 0. It's just how far a number is from 0 on the number line. So if we have a number line, 0 in the middle, we have the number 5. The absolute value of 5, or the distance the 5 is from 0, is 5 units. If we had -2 here, the distance the -2 is from 0, or the absolute value of -2 with these vertical bars, is also positive. It's 2 units from 0. So with distance, we're not going to talk about having negatives if you go into any kind of physics classes, you'll see that we use negative to talk about direction. We're not talking about what direction it is from 0, we're just talking about the distance. So we always want these to be positive. That's as long as there is not a negative out in front of the absolute value. So let's go ahead and take a look at some examples just so you can see what that would look like. So we want to go ahead and find the absolute value. Number 1 here, we're given the absolute value of -9. So how far is -9 from 0? It's 9 units away. Number 2, the absolute value of 9. This one's also 9 units from 0. So if it's positive, it stays positive. If it's negative, it becomes positive. This next one is where we'll have negatives in our answer. So we want the opposite of the absolute value of 15. So the absolute value of 15 is 15, but we want the opposite of that, so we get -15. Now the opposite of the absolute value of -9. The absolute value of -9 is 9, and we want the opposite, so -9. This next one, think order of operations. So, let me fix that. Number 5, we're given the absolute value of 9 minus 4. And so we don't want to change this minus sign to a plus sign. What we're going to do first, think of PEMDAS. Absolute values are just grouping symbols. So we have to do what's inside first before we can evaluate absolute value. So we're going to keep the absolute value. 9 minus 4 is 5. And the absolute value of 5 is 5. So be really careful. It's a really common one where I'll see people changing this minus to a plus. Don't do that. Number 6, we have the opposite of the absolute value of 32 minus 2. So again, simplify on the inside, keep everything else the same. So keep the minus, or the opposite of, keep the absolute value. 30 minus 2 is 30. Sorry, 32 minus 2 is 30. The absolute value of 30 is 30, and the opposite of that, so -30. And one final one here, just so you can see all the different negatives. We have the opposite of the absolute value of the opposite of -2. So we have some parentheses inside our absolute value. So remember, work inside out. So on the inside of the absolute value, the opposite of -2 is +2. So now keep everything else. We have the opposite of the absolute value of 2. And so the opposite of the absolute value of 2 is -2. All right, so now next time we're going to get into adding and subtracting real numbers, so working with positives and negatives, adding and subtracting them. So we'll go ahead and stop there.